This is part 9 of a series on support vector machine. In this video, we will look at the linear support vector regression. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. In this and the next video, we will look at the support vector regression. In this video, we will look at linear regression, and in the next video, we will look at nonlinear regression. Create an objective function for linear regression, as well as Lagrange, Primal, and dual functions, and the constraints. We then solve the QP problem for the dual function to finally generate the decision function. This decision function can be used to predict the target values for test data. We will implement a linear SVR from scratch using CVXOPT. And we will also implement it using scikit-learn's SVR. Let's consider a regularized linear regression problem. Regularized linear regression requires two goals to be considered. One is to minimize the overall errors, and the other is to make W's small. These two goals are a trade-off and must be balanced properly. To achieve both goals, you can use two expressions as follows. This is a regression line or plane, and epsilon is the error of each data point. The objective function we looked at in the linear regression video was like this. The main loss is to minimize the overall errors. However, focusing only on minimizing the errors can lead to overfitting. Therefore, we add a regularization or penalty term to prevent W from becoming too large. Our goal is to find a regression line that has minimal error but is as flat as possible. This is the objective function we looked at in the linear regression video. Let's write this in another form. The main loss is to make the parameter W smaller. In other words, it makes the regression line or plane flatter. However, if you focus only on this, underfitting may occur. So a regularization or penalty term is added to prevent the errors from increasing. Our goal is to find a regression line that is as flat as possible, but with as small errors as possible. Both expressions can be used for linear regression. Support vector regression uses the latter expression. Next, we will create an objective function for support vector regression. There are training data and regression plane in a three-dimensional space as shown below. For convenience, we will call the regression plane the regression line. Set the epsilons, the error tolerance range above and below the regression line. Let's call this dotted line that shifts the regression line by positive epsilon, the positive boundary. And let's call this dotted line that shifts the regression line by negative epsilon, the negative boundary. All data points between these boundaries are considered error-free because they are all within the error tolerance range. The data points outside these boundaries can be said to have errors, i.e. zetas. The epsilon is a hyperparameter and is common to all data points. The zetas are slack variables and are assigned to each data point. The data points between these boundaries have no errors, so their zetas are all 0. The data points outside these boundaries have zetas greater than 0. The error of a data point above the positive boundary is called zeta, and the error of a data point below the negative boundary is called zeta star. Zeta and zeta star are slack variables and are both greater than or equal to 0. Now we use these errors, zeta, to generate an objective function like this. This is the second expression on the previous page. The main loss is to minimize the overall W, which are the parameters of the regression line. Focusing only on minimizing W may result in underfitting, so a penalty term is added to prevent the sum of the errors from becoming large. Our goal is to create a regression line that is as flat as possible, but with as little overall error as possible. Now let's create the constraints. Y is the actual target value, and this part is y hat, the predicted y value. Y minus y hat is the actual error. The actual error should be less than epsilon plus zeta. This data point satisfies this condition because zeta is 0 and the actual error is less than epsilon. This data point also satisfies this condition because the actual error is epsilon plus zeta. Likewise, all data points below the regression line also meet this condition. Zeta and zeta star are greater than or equal to 0. This then becomes a constrained optimization problem. We can now solve this optimization problem with QP to find the parameters W and B of the regression line. Next, let's create the Lagrange primal and dual functions for this optimization problem generated on the previous page. This optimization problem has 4 inequality constraints as follows. This is the objective function. And we can write a primal function like this using Lagrange multipliers for the 4 constraints. Eta, eta star, lambda, and lambda star are Lagrange multipliers. They are all greater than or equal to 0. Differentiate the primal function with respect to W, B, zeta, and zeta star. Then we can get the following expressions. Apply these equations back to the primal function. It is then summarized as follows. If we use this equation, then this, and this disappear. This is because this expression becomes 0. If we use this equation, then this, and this disappear. This is because this expression becomes 0. And if you use this equation, then this and this disappear. Now we can create a dual function like this by replacing W in the primal function with this expression. The variables of the dual function are lambda and lambda star. And the constraints of the dual function are as follows. The first constraint comes from this equation. And in this equation, C and eta are both greater than or equal to 0. So lambda is less than or equal to C. Likewise, in this equation, lambda star is also less than or equal to C. These are the constraints of the dual function. Therefore, the dual function becomes an optimization problem with 1 equality constraint and 4 inequality constraints. If we find the lambda and lambda star that maximizes the dual function, We can find W from this equation. And once we find B, we can generate the decision function as follows. We'll look at how to find B later. Now to solve this optimization problem, let's convert it to the standard form of QP. Maximizing the dual function is equivalent to minimizing the negative dual function. The standard form of QP is as follows. As we did for support vector classification, we define the matrices as follows. The dot product of the data point I and j is defined by matrix K. And alpha is defined as the lambda matrix. This is an example where the number of data points is 2. And the remaining matrices are defined as follows. If you input these matrices into the standard form of QP, you can easily check that it is identical to the dual function above. Using this standard form of QP, the solution can be easily obtained with the CVXOPT library. Lambda and lambda star are the solutions to this problem. Then we can find W using lambda and lambda star. Now let's find B. Let's look at the second KKT condition, complementary slackness, for the primal function. The following equations hold by complementary slackness. This is what we looked at in convex optimization and SVM classification. Let's look at the figure below. Red data points are outside the positive and negative boundaries, and their lambda and lambda star are greater than 0. We will check this in the code of the next page. And the zetas of the red data points are greater than or equal to 0. The data points on the positive and negative boundaries have a zeta of 0, and the data points outside the boundaries have a zeta or zeta star greater than 0. And the lambda and lambda star of the data points between the positive and negative boundaries are both 0. In this equation, if lambda is greater than 0, this part will be 0. Among those with lambda greater than 0, those with zeta of 0 are on the positive boundary. This is because the actual y minus y hat plus epsilon is equal to 0. For example, this data point is on the positive boundary. Likewise, in the second equation, among those with lambda star greater than 0, those with zeta star of 0 are on the negative boundary. For example, this data point is on the negative boundary. Based on this equation, the third equation can be written as follows. If this part is 0, zeta is greater than 0. That is, if lambda is c, zeta is greater than 0. These data points are outside the positive boundary. Likewise, if the lambda star is c, the zeta star is greater than 0. Let's find B using these conditions. These are the constraints. According to the conditions 3 and 4 on the left, if lambda and lambda star are less than c, then zeta and zeta star must be 0. These data points are between the positive and negative boundaries. The data points that satisfy these conditions have zeta and zeta star equal to 0. Then you can see that the equations below are established based on the conditions 1 and 2 on the left. Using these formulas, B can be obtained as follows. Find the data points x and y that satisfy this condition and enter them into this formula. Then we can find B. there can be multiple B. Their average value is the final B. Although we can calculate B using a single data point that satisfies this condition, we use the average of multiple B for stability. I referred to this article. Next, let's implement a linear SVR from scratch using CVXOPT. The data we will use is like this. This is data with noise added to the straight line, y equals 0.5x plus 0.3. We created 200 pieces of this data. Set the epsilon, the error tolerance range, to 0.2. And set the regularization constant to 2.0. N is the number of data points. Let's use quadratic programming to find lambda and lambda star, the solutions of the dual function. To express the dual function in the standard form of QP, we construct the matrices as follows. Then input the matrices into the QP function of CVXOPT solvers and perform QP. The solution to this problem is contained in this variable. Lambda and lambda star are the solutions to our dual problem. Find W using the lambdas and lambda stars. The formula for finding W is like this. X is the training data. Now let's find B. Find the data points x, y that satisfy this condition, and use this formula to calculate B. And find the data points x, y that satisfy this condition, and use this formula to calculate B. Then we calculate the average of B, and this is the final B. The data points with lambda and lambda star greater than 0 are support vectors. Finally, we visualize the data, decision function, and support vectors. This is the formula for finding the decision function. The results are as follows. This is the result when epsilon, the error tolerance range, is set to 0.2. The regression line and the positive and negative boundaries are like this. And all the red data points are support vectors. Again, the lambdas of the support vectors are all greater than 0. This is the result of setting the epsilon to a slightly larger value of 0.6. There is one support vector here. You can see that as the epsilon increases, the regression line becomes slightly flat like this. Next, let's find the regression line using scikit-learn's SVR. Create a SVR model. Specify the regularization constant C, and specify the error tolerance range, epsilon. And we specified the kernel to be linear. You can create a nonlinear SVR model using RBF or polynomials in the kernel. We will look at the nonlinear SVR in the next video. W and B can be found this way. This variable contains lambda of support vectors, and this variable contains the index of the support vectors. Now let's visualize the data, decision function, and support vectors. The results are as follows. The results are exactly the same as the CVXOPT results on the previous page. When the epsilon is set to 0.2, the parameters are the same, and the positions of the regression line and support vectors are also the same. The results are also the same when epsilon is set to 0.6. Let's run this code. The results of CVXOPT are like this, and the results of SVR are like this. So far, we have looked at the linear support vector regression algorithm and implemented it from scratch. In the next video, we will look at the nonlinear support vector regression.